All right, and now we have Marco for the last talk of the day about a very related topic about memory safety preservation for WebAssembly.
Okay, thank you very much for staying with me until the end. I'll try to make this light and funny. So today I'm going to talk about memory safety preserving compilation for WebAssembly, and this is joint work with Marco Patrignani. So I'm going to start my talk with a question. So we have cryptographic code, video rendering, and game engines. What do they have in common?
Need for speed.
Yes, they do, and that's why they're all implemented in low-level languages. They're all implemented in C and C++, and these, as you know, these are memory unsafe languages. And as a result, these programs may have bugs that lead to security vulnerabilities. But they also have another thing in common. All these programs, they get compiled to WebAssembly and executed in web browsers. As a result of that, code that we actually run on our browsers contains bugs and security vulnerabilities. So this work aims at designing a class of memory safety preserving compilers for WebAssembly. In particular, our approach is principled. So we want to actually be able to prove that these compilers are memory safety preserving. We propose two solutions. The first is a short-term solution and relies on existing WebAssembly features for enforcing module-level memory safety. The long-term solution instead aims at compiling C code to a memory-safe variant of WebAssembly, where we can enforce a fine-grained memory safety. So for the rest of the talk, I'm going to give a brief overview of WebAssembly, the features that are relevant for us, and show how these memory safety vulnerability at the source get translated to the target, and then illustrate our solutions and our notion of memory safety. So for WebAssembly, the two features that are really relevant for this work is that the WebAssembly modules are validated. We cannot just run a WebAssembly module, but first we need to type check it, and only then we get the chance to run it. This already removes many vulnerabilities for our programs. The second feature is sandboxing. WebAssembly provides a sandbox execution environment that protects the memory of the browser and other WebAssembly modules from being tampered with. So a given module cannot corrupt their memory. Now let's look at the problem. We start from say a memory safe C program. And this could be, for instance, written in checked C. That is an extension of C that basically extend the types of pointer with a tag. This pointer is checked, so it's going to be checked at runtime. This pointer is unchecked, and it behaves as a regular pointer. When we run this using a checked C runtime system, the interaction between the safe and unsafe code is secured by the runtime system with respect to the check pointers. Now, if we compile this naively to WebAssembly, we might actually, the compiler might actually allocate all the runtime system data structure in the shared memory, and therefore the untrusted module could actually overwrite these the buffers metadata that are used by the runtime system and break the security guarantees of checked C. So show you how we can tackle this problem on WebAssembly today. So the idea is to provide memory isolation through memory module encapsulation. in particular, when we have a safe module, that is a module that is compiled from the safe C program from before, we can export the shared memory, and we can define the private memory that we do not export. The untrusted module can import the shared memory and write and read from it directly, but it cannot access the private memory. This happens for two reasons. First of all, the untrusted module cannot address this memory. This is the validation step. And secondly, it cannot access the private memory by trying to overrun the shared memory because of the sandbox. Now let's see how the memory isolation, how we can use these module encapsulation to provide the memory isolation. We compile the safe and unsafe code with our secure compiler, and we essentially allocate all the unchecked buffers in the shared memory, and we put all the metadata for the buffers in the checked memory. This memory is not exported, so the untrusted module cannot tamper with it. Now, let's go a little bit more in detail and see how we can actually compile these safe modules. The idea is to translate pointers into some kind of capability that is stored in this private memory. So when we allocate a checked pointer, so this annotation comes from checked C, we basically generate a fresh identifier for the capability, and we, together with some metadata about where we're going to allocate it, how long the buffer it is, and where this pointer is pointing right now, and we return the identifier of the capability. So this is important. All this metadata is stored in the private memory. Now, when in the safe module we look up, we dereference this array, we can just load it because load it from the checked memory because of the assumption that the module is safe. Now, the interesting bit comes when the interesting part is when actually one of these pointer at the source level is passed to the untrusted module. So here, the unsafe, we have a call from the safe module into the unsafe module, where we pass a checked pointer. So this is a pointer at the source level. Target level, we're going to pass the identifier for the capability together with the current offset. Now, what can the untrusted module do with this capability? As I said before, because the sandbox prevents the untrusted module from accessing the private memory directly. So what we do is instead to export a safe API to the private memory. So, for example, we define a safe write function in the target at the WebAssembly level that takes a capability, identifier, PID, an index and a value, and it performs the bounds check that you expect, and only if this bounds check goes through, we do write the value into the memory. Then the safe module exports this API, and the unsafe module can write to checked pointers via the API. So this is the compilation of an assignment that writes into the memory pointed by the checked pointer, and that's why we use the safe API. Now, this approach has some limitations, and the first one is that you might have you might have noticed that this approach requires to recompile modules, in particular untrusted modules, to use the safe API. because as I showed before, now we need to we cannot just we don't have a single address. We need to have the capability and the offset. This in practice is not really a problem for WebAssembly because on the web these modules the source programs get recompiled all the time anyway. The second problem, compiling programs that mix safe and unsafe code. So in this case, we actually have to compartmentalize this program into multiple modules. So this mixing safe and unsafe code is something that actually checkC allows to do, and it encourages to do, so that you can progressively turn unsafe C programs into safe by adding more annotations. The third limitation is performance overhead. First of all, because we create more modules, this will result in more memory-hungry executable. And second of all, we have overhead that comes from the bounds from checking key pointers. However, we conjecture that the JIT could help us to optimize these checks and to remove many. And part of this work is actually about evaluating what is the actual cost of implementing this short-term solution and exploiting the JIT to remove the bounds check. Let me now show you what we plan for the long-term solution. We want to target a language designed with the first-class support for memory safety. In particular, we plan to use MS Rossum, which is a memory-safe variant of WebAssembly. So this is a paper that came out recently, and I just want to give you a brief overview of MS Rossum and its design goals. So we heard from Christina at the keynote a few days ago that a good way to build more secure languages is using abstractions, and MS Rossum gives memory safety abstractions. In particular, segmented memory, which means that the linear memory of WebAssembly is split into segments, and the idea is to allocate each buffer in a different segment. Those segments occur only through handles that are in some sort of capability in the end. MS Rossum proposed at the core of MS Rossum design, we have progressive enforcement of memory safety. The idea is that MS Rossum does not force you to have memory safety. You can decide, depending on your application, whether you want to trade security for performance. And the idea is that as hardware evolves and we get more hardware-accelerated memory safety features, we can get more memory safety for less overhead. Here I'm talking about things like ARM's tag memory, capability machines, ARM pointer authentication, and NPX. The third design goal of MS Rossum is to provide a menu of different flavors of memory safety, including spatial safety, so bounds check, temporal safety, so removing vulnerabilities like use after free, and pointer integrity. Now, these two solutions are somewhat complementary. So at the beginning, we could actually use our short-term solution as a software-based implementation of MS Rossum, and then if MS Rossum becomes this proposal gets traction, and we actually manage to link it to hardware-based with the appropriate hardware, we can actually see MS Rossum as an hardware-based implementation of our short-term solution. Now, let me, in the last part of the talk, I'm going to talk about the memory safety property that we want to consider for our compiler. So, actually, we have two compiles, the short term and the long term, and we want to show formally memory safety, which raises the question: what actually do we want to prove about these compilers? We need to provide a formal definition of memory safety. So this is not a new question. It's something that people have thought long and hard about this. This is Michael Hicks' post, what is memory safety, that actually started a bunch of works in this direction. Quickly, after that, this paper came out, The Meaning of Memory Safety, which tries to give which gives a definition of memory safety, interference. Now, non-interference is a hyperproperty, as we know from the works on secure compilation. Preserving hyper-safety properties is much harder. It's harder than preserving simpler properties. This other paper inspired us to look at a simpler definition. These are micropolicy, formally verified tag-based security monitors. In particular, one of the monitors described in this paper enforce the non-interference-like property that we saw in the previous work. Since safety preservation is simpler and implies and enforces the non-interference, the harder property, this is the definition that we picked for our compilers. So let me give you a glance of on our memory safety definition. Is a trace property definition in which that relies on the fact that pointers and memory location are tagged with colors. Our trace collects interesting events collects events such as reading and writing to memory, allocating, and oops, this should have been a free. So read, write, alloc, and free are the events that are relevant for our trace. And then we define the memory safety as effectively a monitor that takes a trace, and this is the heap. If this monitor doesn't get stuck, then the program is memory safe. Okay. With this property, we can actually capture many variations of memory safety. These include special memory safety, so it bounds and not pointer the reference. Temporal safety. This removes. This includes use after free violation, and in particular also relaxed temporal safety. So relaxed temporal safety essentially tells you it's okay to access memory that has been freed as long as the memory pointed to has not been reallocated yet. We can also talk about fine-grained memory safety, that is memory safety within objects. So these could be structs with different fields, and you could overflow from one field to another. And pointer integrity as well. So using colors, basically we match pointer and locations, and we need to store one extra bit to check whether pointers are still valid and are not, for instance, generated, forged using casts. Now, the secure compilation result that we want to prove is memory safety preservation. As I showed before, we can encode memory safety as a safety property, and among the many criteria that we can choose from, we decide on a robustly safe compilation. Now, let me conclude with some remarks on work in progress and future work. We're still working on our trace-based definition of relaxed memory safety, and in particular, we want to we are curious about whether we can say anything at all about memory safety if we give up pointer integrity. So is pointer integrity somehow special in that? The next step on in our work would be to actually model the semantics of MS Rossum and prove it sound with respect to our trace-based memory safety property. And finally, we are working on a prototype implementation for the short-term solution. So that is the compiler that targets WebAssembly. And there is a lot of work to do, and we for sure would like your help. And we have internship available, so if you like compilers, WebAssembly, please come and talk to us. And with that, I conclude my talk, and I'm happy to take questions. Yes?
Can you say a bit more about what you mean by proving semantics and MS Rossum?
Right, so we've defined what memory safety means with respect to this coloring-based scheme. Now we want to take WebAssembly in the proposal, the paper that I showed before, only describes the design of WebAssembly, but there is no formal specification, so basically we want to connect the two. Yes?
Can you say something about what features of source language you support, for example, function pointers and other stuff?
So at the moment, we haven't thought really about function pointers yet. Our source language basically it's a C-like imperative language with a lock-free, can look up arrays, buffers, and struct as well. That's for the fine-grained memory safety. So that's what we have on the plate for now. No, it doesn't.
I think it doesn't.
So yeah. So it only talks about like buffers. I mean, at least the model doesn't say any. I mean, in the model in their calculus there is no.
Oh, no, so sorry. May not do checks on the pointers, but function pointers, but it has function pointers like C-like function pointers exist.
Sorry, can you
C-like function pointers already exist.
yes. No, but I mean.
They are not checked.
Yeah, fair enough. So let's say the check C runtime system, basically for now it only checks spatial safety, and yeah.
All right, do you have a question? Go for it.
So this may be a naive question because I don't know how it works in Rossum, but what do you do for brackets control flow?
For control flow.
Yeah, and enforcement of this lower bracket of this property.
Right. So that I think we get it for free because WebAssembly, because of the validation of WebAssembly. So yeah, we get we get basically as we heard in the previous talk, control flow integrity. But only, so there is some potential, there can be problems when you have something like a dynamic dispatch. So if you do...
I think for user module calls, so does WebAssembly have a built-in spec for that?
Wait.
Between modules, so
When one module goes into the other, yeah, so... yeah, so these interfaces are typed in WebAssembly and they're checked. So basically, if the two modules, when you link them together, you validate that the interface match up, so that when you call this function, you know how many arguments it expects.
No, but it's about like one module calls the other, this one calls another function, calls back, and that one then returns to the first call instead of the second call.
Even syntactically, there is no return.
So yeah, I would say, I mean, I'm not 100% sure, but I think we get a long way with the fact that the WebAssembly modules are validated type checked essentially.
To be argued over at dinner.
Sounds great.
All right, let's thank the speaker again.